Thanks a lot. Hi, everyone. I'm Dan. I'm here today to help out this little guy. You probably know him, the Dinosaur. If you've ever looked at him on a retina display and looked really closely, you may have noticed that he's a bit sad lately. You see, after all these years, he's still being scuttled on cactus thorns every time a network goes down. But it's not just for his sake that I'll be talking today. A network outage can be game over for your apps as well. So let's show some love to the Dinosaur by making our apps work offline, and everyone will be better off in the end. So a little bit about me before I get too far. I guess Vanessa already said some of the projects I'm involved in: Ember, Glimmer, the JSON API spec, Orbit.js. I'm also the co-founder of the web dev consultancy Cerebras. So let's get started with a gentle guide to offline web apps. Nowadays, most discussions of offline web apps start and end with PWAs, or progressive web apps. The PWA initiative was pioneered by Google a few years back with a goal of making web apps reliable, fast, and engaging. Essentially, PWAs strive to provide a user experience that's comparable with native apps, while retaining all the aspects of the open web, like shareable URLs that we love. Now is a great time to start considering PWAs, because service workers, a key technology required by PWAs, are on the cusp of being supported in all major evergreen browsers, desktop and mobile. Since reliable, fast, and engaging are pretty nebulous terms, Google's developed a checklist to make these goals more concrete, including that the site is served over HTTPS, pages are responsive, look good on desktop or mobile, any size. The app URLs load while offline, highly relevant to this talk. That you can add your app to the home screen, just like a native app. And that the first experience with that app must be fast. There are other requirements. I'm not going to go over every single one. And that's primarily because the Lighthouse Chrome extension does a really good job not only listing those requirements, but also measuring them and providing detailed reports about your app's compliance to that checklist, including its performance, accessibility, and more. There are also plenty of tutorials, blog posts, and videos out there that can guide you along the way to building and improving your PWAs. Like this guide from Google that uses Vanilla.js, or other guides that are framework specific, like this post from Matthew Beal from the Ember core team that can help you build a 100% compliant PWA with Ember in about 30 minutes. And there are plenty of other guides for Angular, React, Vue, and more. I'd encourage you to work within the conventions of your framework and CLI tooling to find a good match for you and your app. At the end of the process, all of this tooling will help you develop the same basic elements of a PWA, which I'll review now. First of all, there's the app shell, which is the minimum viable HTML, CSS, and JavaScript required to bootstrap your app. Service workers are a background script that acts as a proxy between your application and its environment, basically proxying between the main thread of your app and the network layer. Service workers must be registered by your app. Here's an example of a registration of a service worker that exists at sw.js. And here's the contents of that service worker. This is about as simple as you can get. It defines the app shell resources, the URLs to those resources, and tells the service worker to cache those resources when they're when the app's installed, and then the service worker can serve those resources back by proxying fetches to them. Here's an example of a service worker that's listening for the fetch event, and you can customize the code that happens inside this listener. This one is checking the caches to see for whether they match. They have a match in the request, and if so, the cached result is returned. If not, the network fetch proceeds. You can also do fetch first and fall back to cache. Another component of PWAs is the web app manifest, which describes your app to the browser. You should link to it from your HTML, and the contents include the name, short name, description, icons that will be used on your home screen, also a background color that will be displayed before the app shell loads, so that you can provide a continuous experience from the time that app is opened to the time it's fully loaded. So for our friend the Dinosaurs revolutionary to-do list app, we've added the checklist, and we're able to cross off all of the items and get to 100% compliance with PWA. And the Dinosaur's happy. We've saved him from those cactuses. However, there's legitimately one more item that we could add to that list: interactivity. In other words, accepting user input to change application state and then syncing those changes when our app comes back online. For a to-do app in which you can't actually add to-dos or mark them complete, it's pretty unsatisfying. You know it's better than nothing, but not that much better. So web standards have helped us greatly so far. Can they help us here? Perhaps soon. The Chrome team introduced a new web API called Background Sync in 2015. And there are implementations underway in Firefox, Edge, and Chrome, but they're all experimental, and it may be a while before this settles out as a stable API and becomes something that we can rely on in our production apps. Now, luckily, we've still got some time left because we don't want to end on a down note. So if we're going to get to that next level of interactivity and mutability, even while offline, we're clearly going to need some heroics. We're going to take that PWA to the next level and build one that's not only resilient to network outages, but allows for full interactivity. So we need to step back a bit to figure this out in terms of our application's architecture. Let's back way up, look at the architecture of most web apps. On the back end, engineers have virtually unlimited processing power and access to everything in milliseconds. This is power. The Norse gods would probably love back-end engineering. I think Loki invented microservices, in fact. Meanwhile, on the front end, our options are much more constrained, and our job is made much more difficult because of those constraints. Modern front-end engineering, as I'm sure everyone here is aware, is a lot more than adding a nice coat of paint to forms. We often need to manage application state, data records, which usually is done in a layer I call the back end of the front end. This layer can get pretty gnarly if we're not careful. But this is where we need to solve our offline interactivity problems. So what do we need to do to manage offline state in this layer? You might come up with a back-of-the-napkin list of requirements that looks something like this. Need to track and queue changes that happen while offline. Need to generate and assign identities to records, serialize and persist all change sets and queues so that if the browser is closed unexpectedly, then you don't lose all your users' data. Then when your app comes back online, you need to sync your changes back to your server. And of course, that doesn't always go smoothly, and sometimes you'll need to reconcile any conflicts or problems. And perhaps even revert to an earlier state. Now, if you're a developer, and we probably all are, or most of us are here, this probably sounds like a feature list for a tool you use every day, Git. And Git was one of my inspirations when I wrote Orbit.js, which is a data access and synchronization library. Since Orbit stabilized in the fall and guides were launched, we're seeing people using it with every front-end framework. Many of the core packages are isomorphic and work on Node as well. Orbit was originally written in JS, but rewritten in TypeScript. But of course, the packages are shipped with all the standard JS builds, and you can use it with either. So Orbit's use cases go beyond offline. Orbit attempts to solve a number of problems. Client-first development, where you're prototyping a feature without prototyping the back end to fulfill it. Pluggable sources. Orbit's very interface-based, so sources that share interfaces can be substituted for each other. For instance, IndexedDB could fall back to local storage. Most modern web apps involve more than one source of data, often more than two. If you're writing an offline web app, at a minimum, you have browser storage and a remote server, and you probably have an in-memory store, and you might even have data streaming in from other sources like WebSockets or server-sent events. And speaking of the main store, it's really nice to work with immutable data, to be able to fork stores, make edits, and throw away the edits or commit them back, merge them back to the main store, but have total control over that process. And Orbit deterministically tracks changes as they're applied to each source, which enables the ability to undo or redo those changes. And because your apps can work offline, they can also work optimistically, even when they're online. Your apps don't need to be hindered by a delay in the request response cycle. If for some changes, you can be optimistic about their application and then only handle failures as they come up, but show a success immediately to the user. So stepping back, sort of philosophically, Orbit considers all these sources of data that need to communicate with each other. And they all have different data in different forms. So we need to put common interfaces on them, and we need to normalize the data that flows between them. And they also need to communicate with each other. And that's done through events. So sources can be wired up in any order based on their events. And the events allow for some flow control. And the events are promisified, and sources can engage with other sources to delay the fulfillment of a request. And then through that chain of requests, then a single request may not succeed until that whole chain is successful. And the Git inspiration really shows in the change tracking, in which immutable operations are stored and tracked according to an ID, just like commits in a branch's history. Every source essentially has a branch with a history, and that history, of course, can grow, and that can be truncated when everything lines up. But you can always tell the differences between different branches or different sources, and essentially cherry pick between the branches or the sources, and keep things in sync, and create new forks or discard them. And immutable data features strongly in this, especially inside the memory store, which uses immutable data structures to cache the data, and which allows for cheap and fast forking. So Orbit has a lot of parts. There's a core library, Orbit core, which I'm not going to go into too much today, but essentially it has a lot of primitives that allow for the history tracking, and essentially the async event coordination. So you could use it to think of it like an async redux almost. But at the data layer, it gets more concrete. This is where some opinions are layered on top of Orbit to actually make it useful in applications. So there's the notion of a schema that's shared among sources, and that schema defines models, relationships, and keys, not unlike a database schema. Every single source in Orbit data has a schema, a log of transforms that have been applied to it, and a couple queues that can queue up async requests and sync events. And then there are optional interfaces. These are dependent upon the capabilities of a particular source. So only some source, you can only directly query some sources. You can, almost all sources can sync with each other. So the interfaces that you would interact with most are the updatable interface and the queryable interface. The updatable interface basically supports a single method update, which takes a transform, and that transform has an ID, It can be assigned a label, so you can actually, could display that label if it's queued up. You could display that in your UI. You could say what went wrong, so you can attach some metadata to this transform. And transforms consist of an array of operations. Those operations might be, in this case, we're adding a planet, the planet Jupiter. We're adding the moon Io, and then we're adding Io to Jupiter as in the moon's relationship. So, and that set of operations can be compounded into a single transform. Now that's not very friendly to write, so there's a builder interface to make that easier to construct. The queryable sources allow for query expressions to be passed to a query method, and again, these could be labeled. This is the raw form of a query expression, and this is the builder form. Here we're requesting all the planets and sorting them by name. Now, something to focus on here is that all the sources that say implement the queryable interface in your application are able to understand the same query expressions. And so you can make a query against the memory store in the same way you can make a query against your backend remote store or your in-memory store. So they speak a common language, and they have a common understanding about the normalized data that they're working with. And to get them all to talk to each other, that's where the coordinator comes in. The coordinator works with sources and applies strategies to those sources. For instance, this is adding a strategy to sync everything that happens to the store to the backup source, which might be, an IndexedDB source. This is an example of optimistic updating, where a request strategy is added so that before the store is updated, we're going to push that update to the remote source. If we had added a blocking true to that, it would turn into a pessimistic update, because essentially this is now saying that the store won't be updated until the remote's push event has completed successfully. So depending upon whether you want to be optimistic or pessimistic, you can customize your strategies, and you can write your own completely custom strategies that are have their own JavaScript logic here. So but there are just some that are provided for convenience. Of course, things do go wrong, especially it'd be irresponsible to not have some failure handling in offline scenarios or optimistic updating. And so you might need to write a strategy that responds to a failure event and takes an action. Like this here is responding to a network error on the remote source, and it will retry the queue of actions every 5 seconds. In this scenario, we're communicating back to the user a failure based upon the label that's put on an update, and then we're rolling back the transform to we're rolling back the store's state to just before that transform was applied. And then we're skipping events on the remote source. So it's basically a reset. We're throwing up our hands Now, we could be a lot more sophisticated about this and do some reconciliation. We're obviously not going to do the same thing as a Git interactive rebase with our users involved in choosing which changes to accept, but we can put a really nice interface on a similar process, or we can just have some hard-coded priorities for which changes succeed in which cases. So something like this might be a fallback when you've gone through all your custom handling. And finally, this is an example of pulling all of the records out of a browser storage source, named backup here, and then syncing those with the store before the coordinator's activated. And activation, it basically activates all of the strategies so that Orbit's coordinator starts to watch everything and keep it all in sync. So getting back to our PWAs and applying Orbit to keep them interactive, what does that look like? What's our strategy here? Well, the Orbit PWA still needs a service worker. It needs to handle caching and fetching of the app shell resources, but it does not typically intercept API fetches because those can be queued up by Orbit on the main thread or on a worker thread. They don't need to be proxied in the service worker. You might have sources like a store, a backup source, which probably would be IndexedDB, and a remote source, maybe a JSON API source. You might even want to add a real-time source like sockets or server-sent events. And then the process for booting in Orbit PWA. The app shells fetched from the service worker when offline. The stores populated with data from backup, like the example I showed earlier. And then the coordinators activated, and all the strategies are activated along with it, so Orbit can keep monitoring things. And those strategies might be something like this. So every change to the store is synced to backup. Every change that happens that's observed on the remote source syncs to the store. Every time the store is queried, a request is made to the remote source, and same with updates. So all of this allows us to finally check off that last item on our to-do list. And it also allows us to add a whole bunch of more items, a whole bunch of more capabilities for our app, whether it's offline or online. And I think the Dinosaur is happy. If you're interested in Orbit, the guides are at orbitjs.com. I'm still working to fully flesh out the site, but I hope it can get you started. And please feel free to follow Orbit on Twitter if you're interested. Thanks very much.